Thermochemistry is the study of energy changes associated with chemical reactions and physical changes. After watching the following videos, students will be able to understand the interconversion between different forms of energy and how they relate to the law of conservation of energy. You'll be able to differentiate between systems and surroundings, as well as endo and exothermic processes, and you'll be able to perform calculations relating to the internal energy of a system and how it relates to the heat and work associated with that system. Energy, as we understand it, is the capacity to do work or produce heat. The energy in our universe is constant, therefore providing us the law of conservation of energy, which states that energy can be interconverted from one form into another, but cannot be created or destroyed. This interrelationship or interconversion allows us to take things like chemical energy from, let's say, a fuel source and utilize it to convert into some sort of mechanical energy that can therefore be used in a different way. Now, all energy can either be defined as being potential energy or kinetic energy. Potential energy is associated with an object's position or its chemical composition, while kinetic energy is the energy due to the motion of a specific object. Now, kinetic energy is going to be directly proportional to the mass and the velocity of the object that's being observed. So the two ways that energy can be defined in a generic way are either being potential or kinetic. And as we said earlier, the energy of a system, or the energy of our universe, is constant. So the interplay between the potential energy and kinetic energy of our system depends on situational application. Let's go ahead and let's look at the kinetic and potential interplay between this red and blue ball. Okay, so we have this red ball here that has potential energy. It's set up on a pedestal and it's basically has a stored amount of energy. Okay, now as this ball starts to roll down this hill, the potential energy that it possesses is going to be converted into kinetic energy. And as the ball rolls down that hill, the kinetic energy is eventually going to be transferred into this blue ball once the red ball strikes it. As the red ball strikes this blue ball, it transfers that kinetic energy, and that kinetic energy causes the blue ball to move on to this platform here. Okay, and the final resting state that we have of the red and blue ball is seen here in this model. Now, if we look at this model, though, notice that our blue ball is now in an elevated position than it originally was. Okay, it's no longer moving, so but it has now more potential energy than it originally had in its initial position. Okay, conversely speaking, okay, the red ball now has less potential energy than it had originally. So overall, there's been a change and a transfer in the energy of this system. Notice the potential energy that was stored in this red ball has been transferred to the blue ball to give it a new potential energy value as well as a new position in the actual chart. So if we go ahead though and look at the overall energy exchange, I think it's very easy to see that the overall energy possessed by the final position balls is drastically different than what would be expected over here. If a complete energy transfer were to have occurred between these two balls, we would have expected this blue ball to have reached a higher plateau than what we see here. Okay, and the reality of it is that there isn't a direct transfer because the red ball is actually moving along the surface. Okay, so additional energy transfer is occurring between the environment and the balls. The balls themselves are not the only things that are exchanging energy. So there are two typical methods of energy transfer. You either have work or heat. Now, work is force acting over a distance, okay, and that's the interplay that we see between the red and the blue ball. The red ball is doing work on the blue ball to give it its new position. Now, as we said, if that was a one-to-one relationship or a direct relationship, we would expect the blue ball's elevation to be higher, okay? However, there has been some other mode of energy transfer because the potential energy that was possessed in that red ball did not get completely transferred to this blue ball. So, what is the other option? The most likely option is heat, and heat is basically a form of energy that flows between objects due to temperature differences. So what typically happens in a situation like this is that as the ball rolls down the hill, there's going to be heat transferred caused by friction between the surface that the ball is rolling on and the ball itself. So energy, the potential energy that this ball originally possessed, is going to be lost both in the form of work and in heat transfer onto the surface of the hill. A state function is basically a property that allows us to determine the state of a system regardless of how that state was achieved. So basically, we ignore mechanisms, we ignore routes that were taken, we ignore procedures for state functions, and only look at their current state. And we can compare two different state functions if we know their initial and final states. It doesn't matter the route that they took. Now, we look at these two hikers and we can compare them. If their position is a state function, notice that the routes that they took to get to their position from their initial state are drastically different. However, because this position or the system is a state function, we can ignore the meandering route versus the more direct route that was taken by each of the individual hikers. So in the previous example that we looked at, the energy of the red ball and the blue ball, the overall energy of that system is a state function. It doesn't matter how their exchange of energy occurred. It didn't matter if energy was lost by frictional heating or if it was lost through work, whatever the process was. All that matters is the final state of that situation or that system. Now, what you must understand is that energy in that situation is a state function. We can ignore the route. Heat and work, however, are not state functions. So you would, if you were asked questions about heat or the work of that system, you would need to account for their actual procedures. So we've been using some vocabulary that needs to be more clearly defined. So yeah, basically, chemical energy is the potential energy associated with chemicals. So methane or propane or the gas that's in your fuel tank in your vehicle, these are all examples of chemical energy. There's potential energy in the bonds of those molecules. So when we look at CH4 or methane, we know that it has potential energy. It has the ability to create heat or energy in the form of heat. Now, in order to analyze chemical energy and chemical reactions, so things like this, we must be able to identify what we're looking at. And describing what we're focusing on gives us the opportunity to be able to clearly discuss what's actually happening with respect to the chemical energy of that reaction. So let's first look at our definition. So a system is a part of the universe in which we're focusing on. So the system might be the container in which the reaction is occurring. And usually for chemical reactions, it is the container in which the reaction is being held. The surroundings include everything else in the universe, so everything that's surrounding whatever we're focusing on. There's also different system types. There's open systems, and with an open system, heat can be exchanged as well as mass or matter, so things can leave the container. A closed system doesn't allow for the mass exchange to occur. Because it's closed, only heat can be exchanged. And an isolated system is one in which, theoretically, neither heat in the form of energy or mass of the substances inside the container would be able to leave. So the system, remember, is a thing that we're focusing our attention on, and our surroundings is everything else that's not part of the system. And this is going to be important for us to understand heat flow, energy exchange, and things of that sort. So if we're looking at a chemical reaction and we're focusing on the system, the heat exchange that may occur is going to be described in one of two ways. It's either going to be exothermic or endothermic. An exothermic is a reaction that gives off heat or that evolves heat. Now, an exothermic reaction is going to be losing energy, in the form of heat. Now, if we're taking our previous slide and we're thinking about the system, okay, a reaction container that has an exothermic reaction, it is going to get warm. It is going to release heat. An endothermic reaction is a reaction that absorbs energy in the form of heat from the surroundings. Okay, so in those situations, in terms of an endothermic reaction, a lot of times heat is going to be being pulled from the surroundings into the system. So why is this important? Why do we need to think about this? Well, all of the interplay that we've just discussed between potential energy, kinetic energy, work, heat, all those are directly related to chemical energy. So instead of looking at the interplay between the position of the red ball and the blue ball, in this situation we're going to look at the differences in energy between reactants and their subsequent products. And basically what we have here are just little mini energy diagrams. Please notice the energy arrow on the left-hand side of both of these reaction types. The representation here shows how we go from having a certain quantity of potential energy, either higher or lower, in those chemical reactants, and how that subsequently plays into the production of heat or the absorption of heat in the specific reaction being viewed. So let's go ahead and look at the exothermic reaction here. Notice my reactants are starting out at a higher energy state than my products. Okay, so when I go from reactants to products, basically energy is going to be being released. In this situation, energy is being released in the form of heat. So the transfer or the energy change that we see from between reactants and products is conserved because some of that energy is given off to the surroundings as heat. This conservation can be better diagrammed if we look at the endothermic or an endothermic reaction. So the reactants in this case are of lower energy than the products. Okay, so in order for us to go from a lower energy reactant to a higher energy product, energy must be put into the system. So in this case, we're looking at an endothermic reaction because that energy must come from somewhere. So energy is absorbed from the surroundings in order to give us our new higher energy products. So the interplay, or that law of conservation of energy, is directly related to our reactant and our product states, as well as whether heat is absorbed or expressed from the reaction type. So exothermic reactions are going to evolve heat, so they're going to give off heat because we're going from reactants that are in higher energy state to a lower energy state. And endothermic reactions are going to absorb heat from the surroundings because we're starting with lower energy products and wanting to get into higher energy product states. So this interplay is diagrammed nicely here with respect to chemical energy. It's the same concept as seen with the red and blue ball that we saw earlier. However, this is more useful with respect to chemistry and subsequent chemical reactions that we may be looking at. The internal energy of a system is the sum of all the kinetic and potential energies of all the particles that are in a specific system. So whatever you're focusing in on, that system's internal energy is going to be related to all the particles' kinetic and potential energy features. This delta E that you see here is the change in internal energy of a system. And that can be represented by the equation here, which shows that the change in internal energy of a system is equal to Q plus W. Q is the heat exchange between the system and the surroundings. Remember, the system is what you're focusing on, and the surroundings is basically everything else. W represents the work that is either done to or by the system that you are applying your focus. So, now, the thermodynamic quantities that we're going to be looking at are always going to have two components. They're going to have a number and they're going to have a sign. The number indicates the magnitude of your change, and the sign indicates the direction of change. And we are going to be looking at these values with respect to the system. Other sciences look at it from a different perspective, but in terms of chemistry, and most chemistry texts are going to look at it with the perspective of the system being the thing you're focusing on. So remember that our change in E is dictated by the sum of the value of Q and the value of W. And Q represents heat and W represents work. So when work is done by the system, so when the system that you're focusing on does work onto the surroundings, your W value will be less than 0. So then it'll be negative. If work is done to the system, so if a piston is pressed down or something of that sort is done to the system, your W value for that specific system will be positive. In that same vein or that same thought process, if a system loses heat, your Q value or your heat value is going to be negative. If the system gains heat, the Q value will be positive. So these types of numerical values will be plugged into the equation here, and that will dictate the overall change of delta E. So depending on what happens with the heat and the work, you may have a system that's losing energy or a system that's gaining energy. It just depends on what's actually happening. This problem, they want us to calculate the internal energy of a system undergoing an endothermic process, which corresponds to a 15.6 kilojoule heat exchange, and where 1.4 kilojoules of work are done on the system. Okay, so in this context, we're going to be using this equation. Okay, because we're looking at the internal energy of this specific system. Okay, so we need to look at what's happening to our Q and W, okay, with respect to the system. So Q in this case is going to be a positive 15.6 kilojoules because the system is absorbing heat because it's an endothermic process. And our work value is also going to be positive because the work is being done to the system. So we're going to then take these values and plug them into our equation. So 15.6 kilojoules plus 1.4 kilojoules is going to give us a delta E that is equal to 17.0 kilojoules. Okay, so that's the internal energy of the system. Okay, so whenever you're doing these problems, you want to write out your equation, you want to write out your variables, and then based on the information that they've given you, you're going to be able to figure out the relative signs of your Q and W. Okay, and in this case, remember that because work and heat were added to the system, both our W value and our Q value have a positive sign. The problem that we're looking at here is a pressure volume work type calculation. And basically what we're trying to look at in this type of a question is to figure out how much work is done to or by a system based on the expansion or the compression of a gas. So if we're looking at a system in which we have a gas that's inside a piston, it's going to change in some way. It's either going to expand and work against an external pressure, or it's going to decrease in terms of its overall volume. Okay, it's going to compress based on its interaction with an external pressure. So this pressure volume work type calculation is going to utilize this equation. So work is going to be equal to negative P times delta V. Delta V is representing this change in volume that's occurring within a piston or some apparatus similar. And P is representing that pressure, that external pressure that's being applied to the system. Now, if delta V is a positive value, what that means is that the piston is expanding, okay? The space is increasing. So delta V in that situation would be getting larger. It would be a more positive value, okay? However, it would also be doing work on the surroundings. If delta V is representing what's happening to the system, it's expanding, that would mean that the piston, okay, is also expanding up and acting against an external force. Now we know that when W is positive, work is being done to the system. And when W is negative, work is done by the system. The equation that we see here accounts for this need to have the appropriate signage, and we'll see this in the example calculation that we're about to do. So if we look at what they've given us, so they've told us that we have a gas that's expanding from 46 liters to 64. So our delta V is going to be 64 liters minus 46 liters. We are going from a smaller volume to a larger volume. So our V final minus our V initial is going to give us a positive value. Now, if we look at this equation over here, our delta V value would be positive. If the negative sign was not included in this equation, that would give us a positive W value. Now, a positive W value represents work being done to the system. However, we know that this piston is being pressed up, or this volume here is expanding, and because this is the system, we know that the system is actually doing work to the surroundings. So we know that our W cannot be positive. This is why the equation is written as it is. This negative sign helps facilitate the appropriate signage associated with W. So let's go ahead and finish the calculation up. So 64 minus 46 is going to give us 18 liters. Okay, so these 18 liters is what our change in volume is. Notice the sign is positive. We are then going to plug this 18 liters into our work equation. So W equals negative P, in this case P is 15 ATM, times our delta V, which is 18 liters. Okay, so our work is going to be negative 270 liters times ATM. Now, we could convert this answer here into joules by using this following equation, or this following proportionality. So 1 liter ATM is equal to 101.3 joules. Okay, so this is a conversion factor to kind of know. It'll come up later. But in this case, they haven't indicated what units we need to give our final answer in. So liter ATM is completely acceptable. So with these types of calculations, remember we're utilizing this equation here. Understand that the negative sign in that equation is allowing us to account for the signage, the appropriate signage associated with work being done to or by a system. We just want to make sure that we're identifying what the system is, the appropriate sign for our change in volume. Obviously, if we're expanding, our delta V should be positive. If we're being compressed, our delta V should be negative, and that will subsequently indicate the type of work that's being done either to or by the system. So now we have a problem that's going to be utilizing all of the skills we just learned in the previous problems. We're looking at a balloon that's being inflated by the heating of the air inside the balloon. So basically they're going to give us information about initial and final volumes. So our final volume of the balloon is 4.5 times 10 to the 6th liters. Our initial volume was 4.0 times 10 to the 6th liters. Okay, so we have information about our volume changes of the balloon. We know that heat has been absorbed by the balloon because of that, we know that we have our Q value of 1.3 times 10 to the 8th joules. Okay, so we have volume values, we have a heat value. We've also been given a pressure value of 1.0 atms. Okay, and they want us to calculate delta E. Okay, so they want to know the change in the energy for the process occurring at 1 atm when a balloon goes from 4 times 10 to the 6 liters to 4.5 times 10 to the 6 liters upon the addition of 1.3 times 10 to the 8 joules of energy in the form of heat. Okay, so basically what we're saying is we're taking a balloon and we're increasing its volume by the addition of heat. So the way we're going to calculate this is by utilizing the delta E equals Q plus W equation. Now, I know Q, that was given to us. It's positive because the system is going to be accepting or absorbing heat. W, on the other hand, must be calculated using the equation that we see here. We need to figure out the work associated with the volume change occurring against the constant pressure value. So W is going to be equal to the negative 1.0 atm times our change in pressure, which is going to be delta V, which is equal to VF minus VI. So in this case, 4.50 times 10 to the 6 minus 4.0 times 10 to the 6. That is going to give us a value of 0.5 times 10 to the 6th, or 5.0 times 10 to the 5th for our delta V value. And we're going to plug this in here. Okay, so our work value that we're going to get is going to be negative 5.0 times 10 to the 5th liters times atm. So we now have our work value. We already had our Q value, and normally we would just plug those into this equation here in order to get our delta E. However, the problem that we have is that the units don't match. The units for Q, for our heat value, are in joules, while our work values are in liters times atm. So as I said earlier, there is a conversion factor that allows us to convert between joules and liters times atm. So work is going to be equal to the following times 101.3 joules for every 1 liter times atm. Okay, go ahead and plug those in. Units cancel out there, and our work units are going to be equal to negative 5.1 times 10 to the 7th joules. So now that we have both Q and W in the appropriate units, we plug them into this equation to get our final answer. So what we're going to do there is delta E is going to be equal to 1.3 times 10 to the 8th joules plus negative 5.1 times 10 to the 7th joules. Okay, and this is going to give us an overall delta E value of 8 times 10 to the 7th joules. And this is the energy change associated with this balloon being inflated by the heating of the air inside. So we get a positive overall delta E value right here, which makes sense because the system has absorbed a fair quantity of energy as heat and as it subsequently expanded. So the system that we're looking at has experienced a positive change in internal energy. So When we're doing problems like this, we want to write out all of our variables. We want to make sure we know our appropriate equations, such as this one and this one here. These are going to be important for calculations on quizzes and exams. We want to pay attention to our unit conversions. So we talked about this one right here. Talked about it previously in another slide, and it could be useful in any future quizzes or tests.